Python Interview Question Series. Part 4, Advanced Python, Questions 31 to 40. For students, freshers, and Python developers. Advanced Core Concepts and Architecture. Let's begin. Part 4, Advanced Python, Questions 31 to 40. 10 Advanced Python Internals Questions. Focus on concurrency, GIL, memory management, and contexts. In-depth explanations with structural comparison tables. Question 31. What is multithreading and where is it useful? A thread is the smallest unit of execution inside a process. Multithreading means running multiple threads concurrently inside a single process. Since threads share the same memory space, they are lightweight and fast to create. In the code on screen, we use the threading module to create and start a new thread for our fetch_data function. Now, here is the critical point for interviews. Python has something called the Global Interpreter Lock, or GIL. The GIL allows only one thread to execute Python bytecode at a time, even on multi-core machines. So Python threads cannot run in true parallel for CPU-bound work. However, they are excellent for I/O-bound tasks like making network requests or reading files, where the thread spends most of its time waiting for external responses. Question 32. What is multiprocessing and how is it different? Look at the comparison table carefully. While multithreading is constrained by the GIL to a single core, multiprocessing completely bypasses the GIL by spawning separate, independent Python interpreter processes. Each process has its own private memory space and its own GIL. This means multiple processes can run on multiple CPU cores simultaneously in true parallel. This is perfect for CPU-bound tasks like image processing, numerical calculations, or machine learning data pre-processing. The trade-off is higher memory usage because each process loads its own copy of the interpreter. Use threads for I/O-bound tasks. Use multiprocessing for CPU-heavy computation. Question 33. What is the GIL in Python? GIL stands for Global Interpreter Lock. It is a mutex that exists inside CPython, the standard Python interpreter. The GIL ensures that only one thread can execute Python bytecode at any given moment, even if your machine has multiple CPU cores. Why does it exist? CPython manages memory using reference counting. Without the GIL, multiple threads updating reference count simultaneously would cause dangerous race conditions and memory corruption. So the GIL keeps memory management thread safe. The practical impact is that pure Python multi-threaded code cannot truly utilize multiple cores for heavy computation. You can bypass this constraint using the multiprocessing module, or by using C extensions like NumPy that release the GIL during their computations. Question 34. Explain Python memory management. Python manages memory automatically using a private heap. All Python objects and data structures live inside this private heap. As a developer, you never access this heap directly, Python handles it for you completely. The primary mechanism is reference counting. Every object has an internal counter that tracks how many variables reference it. When you assign a variable, the count increases. When you reassign or delete the variable, the count decreases. The moment an object's reference count reaches 0, Python immediately frees that memory. There is also a generational garbage collector that runs periodically in the background to clean up cyclic references, which are objects that reference each other and would never reach 0 through counting alone. Question 35. What is garbage collection in Python? While reference counting handles most memory cleanup immediately, it cannot handle one tricky situation: cyclic references. Imagine object A holds a reference to object B, and object B holds a reference back to object A. Neither will ever reach a reference count of 0, even if your code no longer needs them. The garbage collector solves this problem. Python's garbage collector uses a generational collection strategy. Objects are grouped into 3 generations, 0, 1, and 2. New objects start in generation 0. If they survive a collection cycle, they move up to generation 1, then 2. Generation 0 is collected most frequently because most objects are short-lived. This generational approach reduces collection overhead significantly. You can inspect and control this manually using the GC module. Question 36. Explain context managers. Context managers are Python's elegant mechanism for guaranteeing that resources are properly set up and cleaned up, regardless of whether errors occur during execution. The most common way to use them is the with statement. Look at the code on screen. We open a file called log.txt using a with block. Inside the block, we write to the file. When the with block exits, whether normally or because an exception occurred, Python automatically calls the exit method and closes the file. This is guaranteed by the protocol. Under the hood, entering a with block calls the enter method. Exiting calls the exit method. You can create custom context managers using a class with these two methods. Always use with blocks for files, database connections, and network sockets to prevent resource leaks. Question 37. What are iterators in Python? An iterator is any object that implements two special methods called iter and next. The iter method returns the iterator object itself. The next method returns the next value in the sequence one at a time. When no more values remain, it raises a stop iteration exception, which signals Python to stop. Look at the code on screen. We call the built-in iter function on a list. This returns an iterator object. We then call next repeatedly to retrieve items one by one. The first call returns 1. The second returns 2. A third call would raise stop iteration. Here is the most important thing to understand: all Python for loops work this exact way internally. When you write for item in my_list, Python silently calls iter on the list and then calls next on every single iteration step. Question 38. Explain virtual environments. A virtual environment is an isolated Python installation directory that is specific to a single project. Without it, if two projects need different versions of the same library, they will conflict on your system. Virtual environments solve this completely by giving each project its own separate package folder. To create one, you run python-m then followed by a folder name. This creates a directory with its own Python executable and pip installer. To activate it on Windows, you run the activate script inside the scripts folder. Once activated, any pip install goes only into this project's environment. Your global Python installation is never touched. Always create a new virtual environment for every project you work on. Question 39. What is asynchronous programming in Python? Asynchronous programming allows a single thread to handle many tasks concurrently without blocking. Instead of waiting for a slow operation to complete, like a network request that takes 2 seconds, the program switches and does other work, then comes back when the result is ready. Python uses an event loop to orchestrate this cooperative multitasking. Coroutines are async functions defined with the async def keywords. Inside a coroutine, the await keyword pauses that coroutine and yields control back to the event loop. Look at the code on screen. We define an async main function. It prints start, then awaits asyncio.sleep of 1 second. During that pause, the event loop is completely free to run other tasks. Then it resumes and prints end. This pattern is ideal for building extremely high-throughput network servers. And finally, question 40, what happens internally when you import a module? When Python encounters an import statement, it follows a precise sequence of steps. First, it checks sys.modules. This is a dictionary cache of all previously imported modules. If the module is already there, Python returns the cached version instantly without any file reading or code execution. This is why repeated imports are extremely fast. Second, if not cached, Python searches through the directories listed in sys.path to find the module file. Third, once found, Python compiles the source code into bytecode. Fourth, Python executes the bytecode, populating the module's namespace with its functions and classes. Finally, this module object is stored in sys.modules for all future imports. This caching mechanism makes Python's module system very efficient in large applications. Thank you for watching. Subscribe to SHR Trinity for more videos, training programs, live classes, and career guidance. Like and share if this video helped you. Stay tuned for Part 5, Python for AI and ML. If you are interested in attending our live training sessions or have any inquiries, all our contact details are displayed right here on screen and are also available in the video description below. Feel free to reach out to us. We would love to have you as part of the SHR Trinity learning community.